Hello everyone. Today we're going to discuss min-max problems. What is a min-max problem? A min-max problem is a problem where you find the minimum and the maximum of and the maximum of a function, let's say f of xy. Now, how do we do that? Let's get some space here and I'll explain how to do it. Xy. Now remember, in algebra 2 we had a parabola. See, a parabola. Function y equals x squared, and how you find the minimum is doing this. The calculus way essentially is to take the derivative and set it to 0. Take the derivative of the function and set it to 0 and find where the minimum is, which is here at 0, 0. Now why dy dx is equal to 0? Well, because the slope at the minimum or the maximum is always 0. If you think about it, it's always 0. It's always a horizontal line. So I hope it's intuitive enough. Now in multivariable functions, it's quite similar, but it's quite similar, but yeah, it's just quite similar. Let's say we have a function f of xy. All we have to do is take the partials and set them both equal to 0, and we would have found the minimum or the maximum of the function. Now we can't determine whether it's actually a minimum or a maximum just yet, but we have tests for that, namely the second derivative test is what I'm going to talk about. But let's do a simple problem to get our minds exercising. A very weird thing to say. So we have this y, x, z. We have this function so this is, I think, z equals x squared plus y squared. Alright, so how do we find the minimum? Well, easy. Let's switch colors. dz dx equals 0, which is also equal to x, and dz dy equals 0 equals to y, right? Derivatives, and all we have to do is solve for them respectively. Y is equal to 0, x is equal to 0, orange is equal to 0, and all we have to do is plug them in, and we get 0, 0. So we get the point 0, 0, 0. That's easy, right? Now how do we determine if it's a minimum or a maximum? So here in this graph, it's easy to tell that it's a minimum. But what if we don't have visual input? Well, one way is to graph it out but I don't think that's an efficient way. There should be broken lines, but oh well. Well, one way is to graph it out, but that's quite inefficient, and we have a much more efficient way to do things, namely the second derivative test. Yay, second derivative. So let's go back to single variable functions. We have y, x, and a downwards parabola, just like my life. Y equals negative x squared plus 9. Excuse me. Anyways, all we have to do is, again, take the derivative. Equal to 0 equals negative 2x. X is equal to 0. Y is equal to 9. So we know that the minimum or maximum, but we clearly know that it's a maximum, but let's assume we don't know that it's the maximum. So let's assume we don't know it's the maximum, but you can clearly see that it is a maximum. So at this point, this point is 0, 9, as indicated by the calculations. Now, all we have to do is take the second derivative. So d squared y dx squared is equal to negative 2x. It becomes negative 2. And that means, this thing means that if second derivative is less than 0 or negative, then our conclusion for single variable functions, because there is a special case when we deal with multivariable functions, but it's almost the same idea. So if the second derivative of a single variable function is less than 0, then we have, and assuming we are given all of this information, then the function has a maximum point. So the thing that we're trying to find or determine whether it's a minimum or a maximum, it's a maximum. Otherwise, it's a minimum. Pretty simple, right? Hopefully you do get everything. Now let's go do the multivariable thingy. Now let's take the same function. Oh no, don't do that. I wish I had better handwriting on this, whatever this is. Y, X, Z, and the function drawing, it looks thicker. Oops, why do I do that? Like it matters. Now, so we clearly know that c is equal to x squared plus y squared, and we know that that when the never mind, that the minimum or maximum or max is at the point 0, 0, 0. Now all we have to do is take the second derivative again. Now I'm not gonna say the special case just yet, but let's just take the second derivative. So we have dz dx is equal to, I believe, to x. Oh no. And dz dy to y. So now this branches off to d squared z dx squared is equal to 2, and we have this weirdo. I'm not sure if the syntax is right. Wait, not syntax. Is it called the syntax in math? Oh well. The xy. Is this how you do it? Because I usually see it in this form, not partial xy. I usually see it in that form, so I'm just gonna use this form to avoid potential controversy. So this thing is obviously 0, and again, now f of yx is equal to 0 because these things are always equal. Let's see. These things are always equal. Then this thing is also dz dy is equal to 2. Now, oops, squared, there. I fixed it. Now, we see that it's positive. Both of them are positive. So you would assume that it's a minimum point. Well, yes. But what is the special case, or not really special case? This is the general case technically. So let me give you the general case. So the general case is that if f of x the second partial derivative, or let me stop talking, all right, and just write, and f of y minus is greater than 0, and then here if elif flex my programming skills FYY minus, should have done this in a different color, squared less than 0, else I'm awfully quiet. F of x y squared is equal to 0. If these, so let's list them one by one. If this thing happens, then we can conclude. So we can conclude that, oh boy, that if f of x or f of y is greater than 0, then this thing is a local minimum. Let me, too bad this is not marked down. local, and then minimum, else meaning if it's less than 0, else it's a local max. So hopefully that is intuitive. All right, so this is the case that we want. Let's pick a colorful color. This is the case that we want to focus on, but these cases are also possible. So let's say we got this case. If we had this case, then this case means that the function has a saddle, and if it's this case, then it's undetermined. Or cannot conclude null, or can't conclude. Alright, hopefully that was helpful, and see you in the next one. Goodbye.